you bombard a sample with X-rays, the electrons, it emits X-rays. It emits two types of X-rays. One is characteristic X-rays, the other one is continuous X-rays. So this is the X-ray emission from any sample. So you have characteristic X-rays and you have continuous X-rays. So what is the difference between them? The characteristic X-rays, they don't give much information. But the continuous X-rays, they don't give much information. But characteristic X-rays, they give some information because the peak position on the x-axis, this is a typical EDX pattern. So when you do EDX, the operator will give you something like this. He will give you a graph. It looks like XRD pattern, but it's not XRD pattern. Okay, they look same. We have the energy on the x-axis and y-axis is the intensity. And we have two things here. We have energy, the peak position on the x-axis, that gives some information, and the intensity gives some other information. You can get two information from this graph. What are they? The peak position on the x-axis, they identifies what element it is. Each element has different energy for the characteristic X-rays. And intensity on the y-axis, it is related to the concentration. If you have aluminum and copper in the alloy, if aluminum is higher, of course the intensity of the characteristic X-ray that is coming from aluminum will be much higher compared to copper. And using appropriate calibration files given by the supplier, the machine can calculate exactly how much copper is there, how much aluminum is there in the sample. But coming to the peak position, just peak position cannot confirm what element it is because, for example, K alpha of one element might be same as L alpha of a different element. As I have shown this in this slide. For example, you found a peak at 2 keV, for example here. And this 2 keV peak can be related to K alpha of this element. This is the element. Y-axis is the element, x-axis is the energy. So this 2 keV can be related to K alpha of this element or L alpha of this element. You understand? So simply, just because you find a peak somewhere which matches with some K alpha of something, it doesn't mean it is that element. The best idea is to find out if L alpha is there, to find out if M alpha is there. You understand? For example, if L series is indicated, K must be there. Because K, L, M, N, right? If N is there, the bottom one must be there. If that is missing, means your identification is wrong. If M series is indicated, then L series must be present. You understand? So you have to have such knowledge because machine sometimes simply assigns a peak to some element. Without, sometimes it can happen, but as a researcher, you have to keep that in mind. Even though the peak matches with aluminum K alpha, whether it is aluminum or something else L alpha, we don't know. So you have to make sure the other peak, try to look for the other peaks so that yes, it is that particular element. Okay? So we can get two things. Peak position identifies the element, intensity gives the composition from EDX pattern. Sample preparation, most of the time metallic samples quite easy, just polish it, metallographic polishing, sometimes you may need etching. So you do polish and etch and just go to the SEM lab. But if you have a non-conducting sample, then you have a problem of charging, then they may have to coat a bit of metal layer on the sample, which sometimes alter your sample properties, sometimes it may not alter. So you have to keep that in mind before doing SEM of your samples. Because many of you are also doing ceramic samples, some of you are doing polymer samples which are not conductors. So they may have to be coated using a gold or platinum or something very thin layer, not really thick layer. When they say gold, don't think they will put a thick layer. After coming back, you can take it. You don't even see it. Okay. And then lastly, we will see fractography. You can see fractured surfaces under SEM, and you can get a lot of information. Most of the time, when you do the tensile test, I know what students do. If this is the tensile test, you break it. So now you have two pieces. Then, oh, it's broken. Then you do this. You try to put it back. Don't do that. Don't do that. Huh? When you break it, keep them separate. Don't try to put them back. Don't disturb the fractured surface. And run to the SEM lab and see the fractured surface without damaging it. If you put it back, you damage the surface. Most of the time, right? It's a human nature. So, for example, if you have a fatigue failure, and immediately after failure, don't put them back. Go to the SEM lab and look under the microscope to see the fracture surface. You can see here, you can see fatigue serrations. Means with each cycle of loading, the crack has progressed so much length. So you can really measure the length of the crack propagation for each cycle. And you can also find out where from the crack started when you look at the fracture surfaces under SEM. And you can differentiate between your sample's toughness, ductility. Whether it is your sample has deformed before failure or it didn't deform, just broke like a glass. Because this is a typical feature of a ductile fracture. This is a typical feature of a brittle fracture. You will see dimple fracture surface, but here you will see something like cleavage, right? You can differentiate between ductile and brittle fractures. So I suggest you, whenever you do impact tests, whenever you do tensile test, whenever you do fatigue test, you do the SEM analysis, fractographic analysis, and here you have to use secondary electrons. You cannot use backscatter, because secondary electrons can give the surface information. So TEM, just I want to tell two things about TEM also. The difference between SEM and TEM is SEM scans the surface spot by spot. That's why it's called scanning electron microscope. TEM, the electrons go through the sample and gives in one click like a photo. Right? Photo, you just click once, then you get the entire image in one go. But SEM is reconstruction of the information you got from spot by spot in the form of two-dimensional image. It is the computer generated image in SEM. But TEM, it's a real image that is actually coming. You can put a photographic plate and get it. Understand? So TEM can give you much more magnification, but as I told you, TEM sample preparation is very tedious. You really have to work a lot to prepare a TEM sample, and after that you will find you have pressed too much so that there are many dislocations. Then the operator will ask you to go and prepare a fresh sample. It happened to me many times. So with TEM, you can see dislocations. These are dislocations in the sample. You can also see dislocations that got pinned by a precipitate. We always study in the composites preparation, right? When you have a matrix, when you have a precipitate, these precipitates improve the hardness of the material, tensile strength of the material. How do they do it? By pinning the dislocation movement. So you can see dislocation loops around the precipitate here, and you can really see it with your eyes and you can believe it. Because most of the time when your lecturer teaches you about dislocation, he will show you an animation made by computer, not the real dislocation, right? But this is the real dislocation, but not at the atomic resolution, but you can see the line. And lastly, diffraction. I was talking about the electron diffraction. For example, if I have an image like this, we have plates. We have two phases, phase 1 and phase 2. Now I want to do the diffraction of this phase. I want to do the diffraction of this phase. I can focus my beam here and diffract it. I can focus my beam between the grains. I can diffract, and I can get the crystal structure of this phase separately, this phase separately. That's why it is called selected area diffraction, SAD. It is called selected area diffraction. And the typical diffraction pattern looks like this. If you want to know how they got the pattern, this is not the time. You can come to me anytime, I can tell you how this kind of spot pattern came out. This is not the sky. I did not take photo from my roof. This is a diffraction image. They are not stars, they are spots coming from each and every plane. You can approach me or any other person who is relevant to diffraction can explain this. Okay. And when you focus your beam on a single grain, you will get a spot pattern like this. But when you focus your beam on many grains, you will get a ring pattern. Why do you get and you have to solve it. This is like a puzzle. You have to solve this spot pattern. You have to solve this ring pattern to find out what crystal structure that has resulted in such pattern, and to find out the lattice parameters. You can really do the calculations and the TEM. And that's all. Thank you very much for your attention.